magnetic field strength, it is the magnetic flux linking per unit area. When you put something in a magnetic field, a certain amount of flux passes through the substance, and that is called the magnetic flux linkage. Now, see this one. Magnetic field strength, the formula is there. B is equal to phi upon A. But it is the flux linking the surface. So give a side heading formula, and then you have to copy this formula.
Done, sir.
So this is the formula, and what phi is standing here, phi is actually magnetic flux, and A is standing for area. So update the same screen.
Done, sir.
So magnetic flux, it is just like when you are having your mobile phone in your hand. When you're having your mobile phone in your hand, it is linking certain Wi-Fi field lines. It is called flux linkage. The whole room contains field lines of the Wi-Fi system, but you have to consider those which are passing through the surface of your mobile. Definition of magnetic flux. The magnetic flux is the product of the magnetic flux density and the cross-sectional area perpendicular to the direction of the magnetic flux density. Actually, this is coming from the previous formula. B is equal to phi upon A. So if you make phi the subject, so you can make a definition of magnetic flux. Phi is equal to B into A. You have to copy this screen.
Done, sir.
So we use the previous formula, B is equal to phi upon A, and we rearrange it to get phi is equal to B into A. Using this formula, we made the definition for magnetic flux. Now, this is the concept which is now coming, which I was telling you, the concept of flux linkage. Now, the concept of flux linkage is the part of the flux which is passing through the material. So if you count all the lines like this, if you count all of them, this is flux. But if you count only these lines which are passing through this material, it is called flux linkage. Flux linkage is actually the part of the flux which is passing through a substance like a mobile surface, like a material, anything like that. We will take area of that substance. When an object is moving, like when you move your mobile, this flux linkage changes. This flux linkage may change, and when the angle is 90, this flux linkage is maximum. So now we talk about flux linkage. The total is the flux, and the part of the flux passing through the material is called flux linkage. You have to copy this screen.
Done, sir.
So this is flux linkage. This is flux linkage. Look at this diagram. So the lines which are passing through the sheet is called flux linkage. And then the surface area is the area in contact. You have to copy now this screen.
Done, sir.
So this diagram shows the idea that some flux is passing through the material, and that is called flux linkage. Now, flux linkage may change as the object moves. This is the vertical position. The flux is maximum. But when the object is inclined, you might have seen people moving their mobile phones when the signals are weak. They raise their hand and move the mobile. The signal changes because the flux linkage changes. Look at this diagram and look at the change in color. Green color is flux linkage. Green color is the flux linkage, while green and yellow together is the flux. So as the sheet moves, flux changes. Now you have to copy this screen.
Done, sir.
Okay. Now we are putting our first approach of dealing this formula. We are taking the plane of the sheet. We are taking the plane of the sheet as the reference. We are taking the plane of the sheet as the reference. This is the angle theta, and this is magnetic field strength. And we are talking about this angle theta. So the sheet is bent. So the formula will become phi is equal to BA sine theta. Now, it may be a solenoid in the coil, maybe a flat circular coil. So N is the number of turns. N is the number of turns. So the formula will be like this: phi, flux linkage. Phi means flux linkage. Flux linkage is directly proportional to the number of turns. So we will introduce N. We will introduce N in our formula, and that will become the primary formula to calculate magnetic flux. Now you have to give a heading, side heading, approach 1. And you have to copy this screen.
Done, sir.
So we have tilted the sheet. It is like a partially open door. It is like a partially open window. And now put the formula. The formula says phi is equal to BA sine theta. What is the purpose of copying this big diagram? Actually to show where the theta is forming, between what two lines we are making the theta. So update the same sheet and put and mark theta.
Done, sir.
Now, solenoid was in our O level, and this flat circular coil is something which is coming more in A level. It is like a circular shaped wire, circles in circles, and this is called flat circular coil. You have to copy this.
Done, sir.
Now, phi magnetic flux is directly proportional to number of turns. Greater the number of turns, greater is the magnetic flux linkage. So when you increase the number of turns, you will get more flux linkage. Now you have to copy this screen.
Done, sir.
Now, n number of turns on the coil. For maximum value, theta will be 90. That means the sheet will be vertical, like a door in the room is vertical. Or minimum when theta is 0, just like when something is flat on the surface, then you can get this value. So already you have copied the formula. So you have to copy now the maximum and minimum value line. You have to copy this bracket only.
Done, sir.
So mathematically, when theta is 90, sine theta, you take math, so it's very easy for you to understand that sine 90 is 1. And for 0 degree, sine 0 is 0. In A2 physics, there are two possible ways to explain something. One is called mathematical logic and second is called theoretical logic. Now, when it's vertical, it's a mathematical way to explain. CI is never impressed when someone is using a mathematical logic. For any concept in A2 physics, there is a theoretical approach and there is a mathematical approach. Now, theoretical, look on the way that if you do not use maths, if you do not look maths and look on the diagram, you can see maximum lines are passing through the sheet. This is maximum flux. But when it is parallel to the sheet, parallel to the field, hardly any line is passing through it. So theta will be 0. So this is a very good understanding point to read that in A2 physics, you always have two options to use. One is mathematical, which is less credited, and second is theoretical explanation. After that, I put my next concept. This is a small but very important concept in calculation, that in a single calculation, if n appears twice, then for its second entry, put n is equal to 1. So when you are solving a question, when you're solving a numerical, and suppose you put n once, and if you put n again, it will be, the value will be taken as 1. You have to copy this concept.
Done.
Now we are moving towards approach number 2. Now this is a new approach. Now area becomes a vector, even though this is not a reality. Area is not a vector, but we can take area as vector if we put an arrow. Vector is
Sir?
something that has a definite direction. So now give us side heading approach number 2 and
Sir.
copy this. Yes. Did you say
Yeah,
something?
I'm so sorry. I don't know. There's some internet problem or something. Can you repeat the things you were saying before the single calculation part?
This one, have you copied
Yeah,
this?
yeah. Yeah, I copied it, but can you repeat the explanation you were giving?
This is the concept here, that when you are solving a question, when you're solving a numerical question, numerical part, and n appears twice. So you put n once, whatever n is there, suppose 200 or 400. In the same calculation, if n appears again, you will well understand when we solve the question, when you apply it, when you get the value of n, when n appears again, for the second time, you have to put n is equal to 1. For the second time, you will put n is equal to 1. So if in one calculation n appears twice, you cannot put both times n 1.
Okay, sir.
So this is the concept.
Yes, I got it. Thank you.
Approach number 2, side heading, and then copy this screen. This is a new concept that area is by nature a scalar. But if you draw a perpendicular arrow on the area will become a vector. Now, this is a temporary case. This is approach number 2. And normally this approach confuses everyone. But as a math student, I hope you can get it. Have you copied it?
Yes, sir, I'm done.
Now, look at this new diagram. Now, area is making a new way with the B, the arrow on the area is making angle theta with the magnetic field. Now, the formula is BA cos theta. If you carefully see, sine theta has been replaced by cos theta. You have to copy this screen.
Done, sir.
Again, there are two types of coil involved. One is called a solenoid and second is called a flat circular coil. Flat circular coil is like that, which you might have seen, which are used for killing the mosquitoes. It's a green color coil and we burn it for killing the mosquitoes in the night. For now, N is there. The formula is NBA cos theta. Cos 0 is 1 and cos 90 is 0. You have to copy this screen.
Done, sir.
If for n number of turns on the coil, NBA cos theta. So actually, this is the formula for a different approach when we have taken a vertical arrow on the surface. But remember, physical situation does not change. Now, how this formula is using cos, it's a mathematical issue that if you switch 90-degree, sine function becomes cos. That is why sine 60 is cos 30. 30 and 60 sum up to 90. So on a difference of 90-degree, sine converts into cos. So now you see one formula is with cos and one formula was with sine. The two formulas are actually the same, only the axis is now 90-degree difference. This is the concept of phase out by 90. So now you have to copy this.
That's
Now, there are two formulas for flux linkage, NBA sine theta and NBA cos theta. Make it clear the theoretical situation does not change. When the coil is perpendicular to the field, phi is maximum. When the coil is parallel to the magnetic field, flux linkage is minimum. So there are two formulas. You have to copy this screen. Now in the paper, until examiner says something else, you always have to use the formula with sign.
that's
Magnetic field of the earth. You have to give a new heading, magnetic field of the earth.
done, sir.
Now let's make our concept here. Our planet, like many other planets in the world, they possess a particular very weak magnetic field, but this magnetic field is present. That is why our earth has a magnetic pole of north, magnetic south, and if we suspend a bar magnet, it registers the magnetic field of the earth. There are many applications of this magnetic field, but this magnetic field is normally very weak. That is why if you put anything of iron on the surface of the earth, it does not get stick to the earth, but it is present in a very seamless way. So this is the first point. You have to copy this introduction.
That's all.
So it means the Earth magnetic field is very weak. This is a pattern of the Earth magnetic field, and this magnetic field spreads out from the planet, and it is noticeable from satellites also. This is not, even though it's not a very strong field. Now you have to give a new heading, electromagnetism, the same chapter. It is one of the biggest, longest chapter in our course. The same chapter, the name of the chapter is magnetic field. You have to give this heading.
That's all.
Electromagnetism. What is electromagnetism? This concept is coming from O-level physics. There was a gap, and obviously between AS was there. So some chapters they have covered in AS for related with O-level. And in O-level physics, this was a chapter called electromagnetism. Magnetism due to current is called electromagnetism. Magnetism due to current is called electromagnetism. What is the concept? When electric current passes through a conductor, it produces a magnetism. So this magnetism is produced when you run current. You have to copy this definition.
That's all.
Now give a heading, origin of magnetism.
That's all.
Now, we have to discuss this concept that how magnetism actually originates. The concept comes when a charged particle moves, it produces a magnetic field. This is one of the mysterious concepts in physics of in its time, that whenever a charged particle moves, it develops an energy field, and this is the magnetic field. So when a charged particle is moving, look at this diagram. If a charged particle is moving, it produces a magnetic field. When the charged particle is moving in a straight line, the magnetic field produced is circular. So now you have to copy this screen.
That's all.
Now, this is the approach. When the charged particle moves in a straight line, the magnetic field produced is circular. Magnetic field produced is circular. Now, you have to copy this screen. And I'm just coming, copy this screen. When the charged particle moves in a straight line, linear, magnetic field will be circular. You have to copy this.
Done, sir.
Now, the parallel concept is there. When a charged particle is stationary, it produces an electric field around it. So when charged particle is moving, it produces a magnetic field. When charged particle is stationary, it is producing an electric field. You have to copy this thing. You have to see first this. This is an electric field. This is an electric field and it is due to a static charge. So let's make the concept. If a charge particle is stationary, it will produce an electric field. And if a charge particle is moving, it will produce a magnetic field. You have to copy this screen now.
Done, sir.
This is the electric field around a static charge. So we make the concept. And now you have to give a heading, experiments to show electromagnetism.
Done.
So when electric current passes through a conductor, it produces a magnetic field. This is electromagnetism. So electromagnetism is actually the magnetism which is produced by electric current. So this is a solenoid. Just a minute, please. Just a minute, please. Now, this is an electromagnet. You can look at the screen. This is an electromagnet and a solenoid. Look at the direction of the compass needle presently. The compass needle is presently showing the magnetic field of the earth. Now, I'm going to connect the circuit. This is the circuit. And look at the direction of the magnetic compass. I'm going to release current. As soon as I switch on the current, you can see the direction of the compass needle changes. What this shows that a magnetic field is produced. This shows that a magnetic field has produced, and this is moving the compass needle. Now, let me switch off the circuit. Look, as soon as I switched off the circuit, the compass needle swings backward. Now, this is a compass needle and there is a solenoid and you have just seen animation on that. So when you close the switch, the compass needle will move and it will show the direction of the magnetic field.
Although electromagnets require current to operate, unlike magnets, they can be deprived of their ability to attract at any time. Although electromagnets require current to operate, unlike magnets, they can be deprived of their ability to attract at any time.
Now, you have to copy this screen.
Done, sir.
Now, right under it, when the switch is closed, when the switch is closed, the compass needle, when the switch is closed, the compass needle moves showing the magnetic field. Showing the magnetic field. So when you close the switch, magnetic field is produced and the compass needle moves. Electromagnets electromagnet got a revolutionary applications, and the reason is there that you can control them and you can control their strength, you can control their direction. So you have to now copy this screen. Have you copied it?
Yeah, sir, done now.
Okay, so we keep it up to here, and we will continue inshallah in our next class. Allah Hafiz.
Thank you, sir.